Everybody has heard about quantum physics, either through school or in popular media. However, for many scientists, quantum physics is one of the most complex aspects of our universe.
Oh, great. Oh boy, what's wrong, Rick? Is it the quantum carburetor or something? Quantum carburetor?
Despite this complexity, today we will be discussing one of the fundamental concepts of quantum physics, the Heisenberg uncertainty principle. Werner Karl Heisenberg was a German physicist and philosopher born in 1901. In 1927, he will soon formulate the Heisenberg uncertainty principle. This principle states that you cannot record the location and momentum of a quantum object, such as a photon of light, at the same time. One or a combination of these two aspects must be inaccurate, or otherwise known as uncertain. The concept can be described by this equation. Delta x is defined as the uncertainty of position and location. Delta p is the uncertainty of momentum. Both are multiplied together and must be greater than or equal to Planck's constant over 4 pi.
Okay, so listen. Do you know Planck's constant?
Do you know the Earth orbits the Sun?
Well, Planck's constant is incredibly important in the quantum world. To understand the Heisenberg uncertainty principle, we only need to know that it is a constant number. Now, to better explore how this equation is applied, we'll be looking at a classic example, the single-slit experiment. For this experiment, we have a laser firing out quantum objects, in this case photons, through a slit and then onto a backboard. The slit is our location, where the photons are traveling through, and our momentum is the spread of those photons, or diffraction. During this experiment, a pattern appears on the backboard. This pattern shows us that our particles of light are behaving as a wave after it crosses the slit. This is known as an interference pattern, where waves interact through constructive or deconstructive interference. This behavior of both a particle and a wave is called wave-particle duality, which occurs in everything in the universe, including you and me. Except because of our size and mass, it is unnoticeable and does not affect us, unlike almost massless quantum objects. Now that we understand the background of the experiment, we can now see the Heisenberg uncertainty principle at play. If we try and work out the path or trajectory of the photon by decreasing the size of the slit, or delta x, the spread of momentum increases, delta p, and vice versa. There is no way to record a precise location without having the uncertainty of momentum increase, and there is no way for momentum to be precise without the uncertainty of position increasing. Now, I hear you ask, why don't we just observe the photon traveling through the slit and map out where it lands? Well, because of the nature of quantum physics and the delicacy of the experiment, even by observing this behavior means that the interference pattern on the backboard doesn't occur, thus ruining the experiment.
Number 3 in a quantum finish.
No fair! You change the outcome by measuring it.
So does this mean we may never be able to fully understand how quantum objects behave? There is still research being done to this day about how to work around the fundamental truth of the Heisenberg uncertainty principle to better understand the universe around us. Now that we've discussed an aspect of quantum physics, next time you see uncertainty mentioned in your favorite show, you know just a little bit more about how the universe works. Thanks for watching.